Hello and welcome to the Big Bang. Here we want to help you choose geometries for convective mass transfer. Convective mass transfer deals with a mass transfer coefficient Kc that lumps together a bunch of hard-to-measure variables. The flux Na is then determined by the single formula that describes transfer from a surface to the bulk solution. The geometry of the surface determines how you find the mass transfer coefficient Kc, and there are many different dimensionless numbers that can help you solve for Kc, such as the Sherwood number. A good idea is to make a table of Sherwood numbers with the geometry on the left and formula on the right. The rest of this video will help you set up the table. If you have a flat plate, you must first calculate the Reynolds number to determine the flow regime. If the Reynolds number is less than 2 times 10 to the 5th power, you have laminar flow, and you would use the top formulas. If the Reynolds number is higher than 2 times 10 to the 5th power, you have turbulent flow, and you would use the bottom formula. If you have a single solid sphere, note if you are performing mass transfer into a liquid or gas stream. There are different approximations of the Sherwood number for both of these cases. For gas bubbles, such as in bioreactors, note the bubble diameter. The cutoff is 2.5 millimeters, and there are 2 different formulas for if the diameter is greater or less than that cutoff. You might see a new formula for the mass transfer rate, denoted Wa, with units of moles or mass over time. The little a is ratio of the area available for mass transfer to the liquid volume and has units of inverse meters or inverse length. You will likely be given the value of a in the problem. Here, another dimensionless number, the Grashof number, becomes important. See Table 30.1 in the textbook for a consolidation of dimensionless numbers. If the Reynolds number is greater than or equal to 0.4 times the Grashof number to the 1/2 power times the Schmidt number to the -1/6 power, then free natural convection becomes negligible. Once you are aware of the different methods to solve for the mass transfer coefficient, solving problems that deal with convective mass transfer becomes much simpler. Now that we are familiar with multiple formulas to solve for the mass transfer coefficient, can you figure out what the units are? Here's a hint. Use the formula for the Sherwood number. I hope this video was helpful, and I will see you next time.